nanohub.org.
Online simulation and more for nanotechnology.
All right. So today we'll be talking about the last third of the course, and it's a good one. This 5 weeks is good, so that it starts quickly and ends quickly. But my goal today it will be to discuss the most exciting thing that people are talking about recently. It has to do with big data, machine learning, and all those things. And one of the things I have often understood by working in the field for in physics and engineering many years, that there is often on new things there is a lot of hype. Once you understand it, you realize that there are positives and negatives, and then you try to use them as appropriate. But in the beginning, there's a lot of hype, and that's not any different for this area. So let's get started. I started by saying in the beginning of the semester that you can view the data, the types of data that we deal with as being small versus large data. And big data is as is, meaning that is pictures from your camera, or it can be the clicks that you make when you buy products. And there are, of course, the Department of Commerce. They keep the census information, weather information. So these are big data, as is. On the other hand, up to this point, up to this 19 lectures, we had been talking about small data, how to design experiments, how to do them in a way so that you have the least amount of experiments done for the most amount of information. So there is that essential divide. And on one example, I started the semester by explaining that, big data, Galileo had small data, because in those cases, in those days, the telescope was not very powerful. This is the first time it was being used to look at some of the things. But of course, although the data was small, the other end of the data was Galileo, and which means that when small amount of data is sort of filtered by a great mind, you can do fantastic things. And that's what that was sort of the beginning of the end of the Ptolemy's model, because if a moon rotates around another heavenly body, that means that its Earth may also rotate around the sun. So that was sort of previously everything. Ptolemy had everything rotating around the Earth. And the big data, of course, Hubble telescope, fantastic data. But here the question you have to ask is, you have to learn to ask the questions, because you're not looking at anything in particular. Here you have to ask where the galaxies are born, or where the stars are born, and whether there's dark matter or not. So you have to learn to ask the questions related to what you are given. You cannot really design an experiment for the universe to tell you any story. And I told you that this big data comes from variety of places, and it is really driven by the memory technology, because this is one thing to have the data, but if you could not save it for analysis at a later time, then that data is not really meaningful. Think about from the beginning of time, all the people who have spoken to each other. And there was a lot of wisdom, lot of emotions, this and that in that data. But of course, nobody wrote it down. There is no tape recorder. There is no recorder of any sort. So therefore, only way we could transmit data is through our genetic information, or through our poems and literature and all our stories. That's how we used to transmit data, or books. After the printing press, the books came along. So the big data is an essential component of the big data. Is not really big data per se, but the ability to capture them and retrieve them at a later time for analysis. That's the essential component of big data. Now, one thing I want to emphasize that, any technique that we learn from big data, it applies to little data also, meaning small data also. There was this, I'm not sure whether this is true or not, that Newton was the inventor of the cat door or the dog door, and for his mother. And the idea was that for larger cat, he had one door, and for smaller cat, he had few more doors, without realizing the larger door could probably accommodate both types of cats, right? So therefore, it's a mistake to many of the techniques that we are using now that are equally well could apply to both principles. This is very important to understand. So just a roadmap of how the lectures have been. First of all, we started with this data analysis, cleaning up the data. We talked about how to sort of best fit of the data. How do you compare two of these, two or more of the distribution functions for better fit to a data? We did all the reduction of experiments, scaling of the input variables, what is it? The pi experiment? Buckingham pi. I was thinking Huffington pi. That will not be a good thing. Buckingham pi experiments, and then we are beginning to talk about how to get the f properly. The thing that is different from before, that here we are not assuming any differential equation, because we don't have any differential equation. Here we may or may not know the physics at all. And so therefore, how do you get a function f when you don't know the physics? So in some way it is pre-physics. It's pre-physics, and we are trying to get the physics of the f, and then gradually, by looking at f carefully, just like Ptolemy did in terms of he had to rely on all the heavenly bodies, accurate measurement by Greek astronomers. So he had the data. So today we are talking about that f, that data, and how to describe them. So Ptolemy's model would be the first model of that data, and that would be f, meaning that it is an empirical model. It fits the data very well, but it cannot make any prediction. Prediction meaning you cannot you cannot predict Halley's comet will come based on the Ptolemy's model. It explains whatever is there very well. So I'm going to have a roadmap for this discussion. There will be 4 lectures, and so therefore I'm going to have a lecture on some of them. This is sort of a roadmap. I think it was created by a group of people. The idea was, let's say you have the data. Then the first thing is the data processing, and then there are a bunch of techniques. And of that technique, this is the technique that I'll be talking about today, is dimensional reduction. So I'll be talking principal component analysis and singular value decomposition, very closely related. I'll not be talking about these two, but you can always Google them and you can find them. But the idea is similar. Next class, I'm going to talk about the supervised learning and regression and classification. These things I'll talk about, and I will do it in the simplest way possible, so that I cannot think of anything out there which is simpler in terms of understanding this. And I will explain how the logistic regression works, how the support vector machine works, and how the artificial neural network works. These are very, very simple concepts. There's nothing to it. And then, the concept, there's nothing to it. Of course, the implementation, there is the whole computer science department is sort of working all over. But the basic concepts are intuitive and simple. And then I'll talk a little bit about this in the next class, unsupervised learning, especially in terms of k-means clustering. So I'll talk about that. And then testing and validation, I'll have several slides on discussing about that. But all of them, if you know one, all of them are closely related. Some variant of the original, just the original idea. So, why do we need reduction in the data? One thing is the classification problem. You see, when you look for something and search for something in the Google, then it does something with your search and with your history of searches, and Google knows a lot about you, that it knows so much that it can give you the advertisement that is tailored for you. Next person sitting next to you searching the same thing will not get the same thing. So what it automatically did, that based on the search, it realized that you belong to a cluster of people. That person may not be a neighbor. That person may be 5,000 miles away. They are a collection of people scattered all over the world, but you are similar. Your habits are similar, and your buying patterns are similar. So this is a classification problem. So all the people, and then that may be true for recommendation also, that if you like this book, you'll like that book. That also based on the classification. Machine learning is great about this classification because its classification is not a projection problem. Because, what is the worst this can happen is that you will not choose what they recommended, but it will learn in the process. So there's no harm done. But if you send a rocket to the moon, and if you make a little bit of mistake, a bunch of people will die. So anytime there is human beings involved and their life and death situation involved, like in in drug discovery and all, one has to be very careful about doing machine learning, because this is not. And then of course you can do machine learning in here. It's a pattern matching, whereas they match about 22 points or 32 points on the face, and based on that they can say this is this person, that is that person, and so on and so forth. So this is a pattern matching problem, again a classification problem, and this is very good. But one thing you may not realize by now, if you use social media, I don't use it that much, but I realize that what is this music service that we use? Spotify. So Spotify, so there is one is classification, meaning unbiased classification, meaning you give the data, you don't give it any other information. But in Spotify and others, there's one extra layer where you say that what you liked. You click on, you train the data, and that's very important. That rapidly increases the accuracy. So Spotify and others, they also, and the reason Netflix is so good, that it allows you, it gives you a bunch of options and say, what do you like? And as soon as you give the information, the classification becomes significantly better. So I will explain that. It's tiny, a little bit, right? So this is the classification problem. So what is the big deal about big data? Big data can do classification. That's the big deal about big data. Now, classification can be done in various ways, and what turned out is an important distinction is that when you are searching for this information, then this has to arrive within a fraction of a second before you click the next link. And that's why algorithms are very important, fast algorithms. So what I'm going to tell you today is the singular principal component analysis, very accurate, and it has been around since probably early 1900s. So people could do that already. But the thing is that it was not as fast. So you can use it in many cases, I'll explain, but even the Netflix, the first competition they had in 2006, they gave $1 million prize for that. The winning entry was also singular value decomposition. So therefore, it's not a non-standard technique. But if you want very fast response, by the way, Amazon used to do singular value decomposition also. But if you want very fast response, then you have to do the second category, supervised and unsupervised. And there you have artificial neural network that runs faster. So this is sort of different things. Depending on the application, you will choose which one you want. That's it. So I'll give you simple examples. So for example, here is two things. For example, this is an homework you will do. This is something my student Shin, he helped me out with this. That if you have, let's say, go in the field and make a bunch of measurement of the gene of certain things, let's say. Then you will have a three-dimensional thing, depending on gene 1, something has gene 1, something has gene 2, something has gene 3, and then, but let's say, when it's three-dimensional, you can still visualize it. But assume that you have 50 genes on something. Then you have 50-dimensional thing. You cannot even draw. And if you cannot draw, then it becomes very difficult to sort of classify that is this set of things different from that set of things. So what is often done is that is what the data dimensionally reduction thing comes from. That you have a high dimensional data, you learn to project it in the low dimensional data, let's say in 2D, and that immediately gives you some clusters, and that tells you that there are 4 things. For example, here, so that's what exactly, let's say, Amazon would do. Amazon you are buying many books, many other people are buying many books, but they will project it and they will find you here. And they will know that you are like those green people. And therefore, they are going to make a recommendation based on what the green people buy from their system. So that's what they will do. There are many other examples. Let me not go through that examples right now, but let me explain the concept. All right, and the principal component analysis, probably if you wanted to think about it in the simplest possible way, is that, this is a 3-dimensional object. A teapot is a 3-dimensional object. If you just look it from the side and send somebody some information about this teapot, that's really will not give that person the true idea about its volume. What you have to do, you have to rotate it in a way. Still, it's a 3-dimensional object and you're projecting it in 2D. You rotate it in a way so that it carries in 2D the maximum amount of information about the 3D. And similarly, this picture, this is sort of many times you have seen that this type of picture where people is essentially it's a drawing on a 2-dimensional surface, but it gives you an impression as if there is a 3-dimensional all sorts of landscape and everything. It's very hard to walk even on this. It gives your brain plays tricks with you that it looks like it's 3D, but it is actually 2D, right? Everything that we see in our cornea and our is always 2-dimensional projection of the 3-dimensional world. So anyway, so this is a wall about data rejection. Principal component analysis is the mathematics that allows you to do this particular rotation that will carry the maximum amount of information. So let me go through a few simple examples. So for example, this particular example, let's say you have a group of students who have done a certain amount of gotten certain amount of marks for English and math, and you want to know whether how are the students ranked in terms of are somebody good or somebody is there a grouping among the students that some of the students are falling behind and some of the students are doing well. So that's the classification problem. And second is that if you wanted to know one by one that who is the best and who is the worst, then you have a group of 1. That's also another classification problem. So it turns out that doing it in 2 axes is already difficult. And if you have, let's say, five subjects and then saying who is the best student, or in the previous case, for example, I had a example where a athlete does javelin, the discus throw, this and that, and who is the best athlete if you had to give it a prize. Then how do you do that? And principal component analysis essentially will be a 1-dimensional projection of this multidimensional data that will capture statistically the best composite of all those things. It will have the best composite. So let me explain how it works. The idea is actually very simple. The idea is that let's say you have a bunch of points. And what you do is you try to fit a line. Generally, we can always fit a straight line through anything. But this is a spatial line. This spatial line is such so that the projection, normally when you do a line fitting, we do a vertical difference and we try to minimize it, right? Least square things. But here you are doing perpendicular projection and you try to minimize the perpendicular projection. And if you do that, and if you are only given one dimensional information that you can transmit, in that case, this is the only axis you will be able to transmit. Of course, if you are given 2, then this rotation doesn't really do you anything because every point xy will have an x prime, y prime. You have the same amount of information, so it doesn't help you. So if you have the same dimensionality as before, of course you can transmit the full data. The question is if you have reduced dimensionality, then what is the maximum amount of information you get? That was how the teapot was rotated, this axis rotation. And so you can do that, and you can immediately see for this example, for example, that you have a bunch of students who are doing very well and a bunch of students who are not doing so well. although you may not be able to say from the marks themselves, in 2D is sort of probably possible. You need to pay attention to these students. So this will probably give you a classification idea also, right? So how do you do that? How do you find this? So what is the question then in this class? Our question is, how do I find this rotated axis? It's not complicated. And second, that how do you use it? How do you use this information? So I will walk through a very simple math, and that is you have done probably many times, but that's there, what is there underneath this, all this principal component analysis. You understand, right? Principal component. So there are, this is one component, that's another component, that's one component, this is one component. So principal component means the component that has the maximum amount of information about those points. Then you have second principal component, you have third principal component in successive layers of lower and lower information content, hence in the principal component analysis. The other one is called singular value decomposition, and that is because is another name. And that's because it has to do, it has a relationship with the eigenvalue of a matrix. So we'll talk about that in a minute. Alright, so what you do here, if you take a vector like this, so what is the vector? 97, 94, 30, that's 1 point, 32, 60, 89, 60. So you put all this and throw it in Wolfram alpha. And Wolfram alpha, then you say, do me a singular value decomposition. And what it is going to do immediately is going to find three matrices, U, sigma, and V. And it is going to come as V transposed. That's what is going to come. It's going to give you this vector. How you got it? Well, they say if you read a linear algebra book, you will get it. But I will explain it, what it means, so that you know that after you get it, how you use it, right? But anytime you put it in and simply say that break me down the singular value decomposition, it will do you singular value decomposition. Now, this sigma stands for this singular. Principal component, or this sigma stands for the singular, so therefore, and the values that it will get will tell you which one is the most important. So this one is the most important. It will tell you that 90% for the information, for example, is contained within that. And then you have sigma 2, that will maybe 6% of the information. Then you have sigma 3. So if you could just send 1, then you will just send sigma 1 related to the sigma 1. Now, how would you know what information to take and how much to rotate? Because that axis, it's saying you there is an axis that will contain most amount of information, but you don't know what the axis is. So how do you do that? So what you do, you take one of these. You take one of the vectors that came in here. That will tell you, I'll give you some examples, that will tell you how much to rotate. How much to rotate. And this one and this one together will give you information about what is the projected value. So no point in doing this math in a complicated way. Always better to look at an example so that everything becomes clear. So you can do it in various ways. This is the idea about how things are being reduced. So let me give you an example. But before I give you an example, I have to remind you that if you want to rotate a vector by theta, then what you have to do, you have to have a matrix. Remember 2D. So that's why you have 2 by 2. If you had 3D, then you have a 3 by 3 rotation matrix. But in 2D, let's do everything in 2D. Everything that works in 2D will work for 3D and higher, and no problem. So you can see in 2D, the first one, you have cosine theta. So if your matrix was 0, 1, minus 1, 0. So cosine theta of 0. So what is that? What is that equal to? How much the theta was rotated by? 90 degrees. Because cosine 90 is 0. Or you can, if you don't want to take a look at that one, you can look at this one also. It's no problem. So sine of 90 is 1. And then therefore, if you have a minus 1, so that's really, so you can take any one of the components and get the theta, because it's essentially describing the same equation. One of them will be fine. If you wanted to do 180, this one will become minus 1. If you wanted to do 270, then it will become 0 again. and so on and so forth. But what you see that at 270, because at the opposite of 90, this angle has sort of gone in the opposite direction. It's like a sine of minus 90, and then you have a plus. So this will allow you to, if you look at this point, any of these, that will allow you tell you how much to rotate. Okay, so let's look at this example. Let us say I have 3 points, and I will make my life easy by sort of saying, so that I know the answer, that these points are 0, 0. That's the first point. It was like English and math, that type of thing. 0, 0. Another point is, so that's that. Another point is 2, 2. Another point is 1, 1. It's not ordered in any way. And so let's say this 2 point. I know the answer, right? How much it will be rotated by? It will be rotated by 45 degrees. That will be my answer. So I'll see how the singular value decomposition tells me that it gives me 45 degrees. Moreover, do you see that 100% of the information would be in the principal component 1. I don't have to send it anything else. And finally, do you also see that in that new axis, the separation would be, here would be square root of 2, this would be square root of 2 over square root of 2, the diagonals. So these are the things I expect. Whatever analysis I do, this is what I expect. So I throw in these numbers and call Wolfram alpha. You can call anything you like. This is SVD, singular value decomposition, and you know how these things are done, right? You have to put this bracket and then put the bracket. This one you don't need. So it will immediately return you this 3 matrix. And so let's think about that, how it goes with our intuition. First of all, do you see that in the sigma matrix, which gives me my relative strength of which my axis is stronger compared to the other one, it is square root of 10 here. So that says that and the other one is 0. So the second axis, second principal component contains 0 amount of information. All the information is in my principal component, 1. So therefore, I don't need the second one. This one is telling me. If it were 9 and square root of 1, then I would have gotten 90% here, 10% here. Okay. Now, let's take a look at this one. This V transpose is actually the rotation matrix. This is the rotation matrix I just said. So 1 over square root of 2, do you remember from trigonometry that, or what theta gives you 1 over square root of 2? 45 degrees. Certainly. And so cosine theta is 1 over square root of 2. And so therefore, it is telling you, you have to rotate it by 45 degrees. Right? And finally, what are these? These is something I have to do a little bit more. You can begin to see that it is already giving you some sort of distance, but not yet. I know the angle it has been rotated to, but then I have to do a little bit more work. What I have to do, so x, by the way, you can call it u1, you can call it u2, you can call it u3, and so on and so forth. And similarly, you can call it v1 and v2, right? Vectors. And you can, when you write it out, those things, you will find that it is given one u1, sigma 1, v1, t. This is that row. And this is the sigma 1, square root of 10. And u1 is a vector, particular vector. And then you have, say, u2, sigma 2, v2. But we know sigma 2 is 0. So therefore, we don't have to worry about it in this particular case. Now, if the sigma 2 is small, then if I throw it out, then of course, I will lose some information in this picture. So I'm doing an approximation in that case. But in this exact case, I have my u1, this is my square root of 10, and this is the v1 transpose. Do you see that? This is that. And so then, what will be my approximation, the new x prime in this direction? All I have to do is essentially, if I take x and just look at the first component, multiply these 3 things, what we will find that I will reconstruct exactly the information, the points that were there. It has to be, because there is no other component is not playing any role, and so therefore, I have exactly reconstructed. So if you have a friend in Mars, you want to send him your picture, in this particular case, sending him just the first component, he will be able to perfectly reconstruct your picture. That's what it means. So this is one thing. Image compression or dimensionality reduction is one function. But it will also have classification, because if these 2 points are close together and this point was farther out, then you could also do classification based on this, right? So here it's just reducing dimensionality, and then classification is following out of that. All right. So I want to know, I know the answers, that how far distant these things are, and all you have to do in that case, you have to take the original x, which was the original points, and you have the v. So if you do x dot v, and the order is very important, it will tell you where on that PC1, the principal component 1, where the points lie. One point lies in 0. The second point, which is 2 by 2, actually on this axis lies in 2 square root of 2. And 1 point lies in square root of 2. We knew that. We didn't have to do any singular value analysis for that one. But it gives you confidence to use the formula correctly. And similarly, you can get the same thing in another way. You can either do x dot v, or you can do u. Remember, the u was the first, this u. So you can do u dot sigma. If you do that, you will get exactly the same answer. This vector is 0, is because on this axis, there is no component at all. That's why this component is 0. And what I did here was a little math. Remember, x was equal to u sigma v transpose. I multiplied on the right a v, and when I multiply a right a v, v transpose v is 1. So u sigma, so this is what u sigma. So this tells you the projected values along the axis. This is what it means. So a little bit, let's make it a little bit more complicated, but not too much more complicated, just to get our intuition right. Only thing I did, I changed 1 point. Instead of 2, I make it 2.1. So you immediately know what's going to happen, right? Answer is going to be close to 45. But this time, it will not be exactly 45, because 2 points are in 45, 1 point is slightly off. And this time, the other singular value, or the principal component, will not be 0, right? Because the other, I cannot really put it on a line. So let's see what happens. Again, you throw it in Wolfram alpha. It gives you those values, 1, 2, and all these things. You put it in. You get a u, v transpose, and you get sigma. Now look at this. 3.226. By the way, previously it was square root of 10. What is the square root of 10? So it will be like a 3.4 or something, 3.4, something like that. I don't remember anyway. But so this would be a little less. It will be a little less, because now this is not the whole thing. There is a tiny component in here. Why? Because I have one axis here. If I just send the transmission of this and project this point onto this one, that information is forever lost. I cannot reconstruct that point back. Not possible, right? I left that information. But nonetheless, if only thing I can do is to send one axis, that's the best I can do. I cannot do any better. So let's go ahead and check whatever we did before. Now this time there is a little sigma 2. If I don't take that little sigma 2, I say I will only send this first component. Then I have u1, which was the first vector on the last slide. Sigma 1, remember, 3.226. And the vt, I multiplied them. And then once I multiplied them, what I'll say that the first vector is 0.098. Little bit wrong now, right? Because it used to be 1. Little bit wrong now. And this used to be 2. But now it is 2.01. And remember, this is what I'm going to send to my friends in Mars. And so therefore, the picture would be a little bit wrong. If I could send him both vectors, then it will again become that person could rotate the vector and get back my picture completely. It is that I'm not going to send this one anymore. That's what the thing is all about. So it's approximate, not exact. And then what will be the projection? The projection, remember, previously it was square root of 2, and then there is a 2 square root of 2, right? That was the projection. But this time, once you do this x dot v or u dot sigma, if you do that, what you'll see that 0 square root of 2, almost, but the other one is not 2 square root of 2 anymore, because it has been projected to the nearest point. It is no longer where it used to be. So the vector has shrunk a little. So bottom line is that this allows you, now you saw it just in 2 dimension. When you are buying an Amazon product, there are millions of rows and millions of, because products, maybe 100,000 products people buy from Amazon. And then there may be 5 million customers. And you have a gigantic matrix. And within a fraction of a second, it wants to tell you if you buy like this, you will also like that. So therefore, it is trying to do, every time you are clicking, there is a matrix entry in the humongous matrix. And it is doing the matrix rotation while you are just still on the page, right? And trying to find who is your friend. I wonder sometimes who my friends would be. I want to take a look. I'm sorry, this spelling is wrong. Principal, right? Principal component analysis. So one is this, that I showed you 2 to 1D, but you don't have to do this. All you have to do is take, just like in here previously I said, 1, 1, 2, 2, or 2.2. So here you'll have 3 coordinates. You'll have 1, 2.5, 3.7, comma separated, and you put whatever number you want, and you put SVD. And the SVD then and it tells you that how many components you want. Previously, I just wanted 1 component. But here, at least 2D, human beings can look at it relatively quickly. So 2D is okay. 3D starts getting complicated. So you put it in least amount of projection possible, and that gives you the components and various components. Now, singular value decomposition is actually very computationally intensive. You can see that, right? It has to find all those eigenvalues. It turns out that if the system was square, the matrix was square, then these things will become, the sigma will become all the eigenvalues. And the u vector will be the eigenvectors, and the other one will be the transpose of the eigenvectors. Composite one. So that is what you'll see Professor Datta and others do in their transport classes. Same math, same physics. Because at the eigenvalue, when you have an eigenvalue of a, let's say, oscillator, you push a little bit, give it a little bit of ping, it continues to oscillate, right? Child on a swing. So that's why it's called singular, because if you do a Laplace transform, it will become a singular at that point. Transfer function becomes singular. That's hence the name singular value decomposition. Of course, the homework problem, I'm sorry, there are many places the spelling is wrong, but the homework problem is I asked you to take your picture and then try to see that at what point they can still recognize you. You of course can recognize yourself with 0 pixel, but ask a friend to see how many pixels they need to recognize you, and the code is also given. The code is given, the picture, everything is given. All you have to do is to just, so here you as Mona Lisa, you just put your picture .jpg and then in here. I assume that it doesn't matter whether it's JPG or not. MATLAB can probably read these things anyway. And then you should be able to do, if you keep 50 dimensions, 15 dimensions, you can change these numbers. Instead of this, you can make it 5. To see you in 5 dimensions whether they can still recognize you. I don't think below 15 or 20 sort of things are not very recognizable. By the way, when you load a newspaper on your web page, this is often what is done because they keep sending successive principal components so that you don't go away from the page because they still is giving you this and then gradually they are refining. In the old web page, we used to sit. It is loading 3 lines, 2 lines, you are loading. And by the time you click on, cut that and go somewhere else. So they have figured out how to keep us hooked. All this math done for this, just for this purpose. All right, so I hope you understood that what a principal component analysis, PCA, not PCR. PCA is a useful tool for reducing the multidimensional data. And the goal of reducing the multidimension is classification. You have to do classification. So that's what, now you may ask, here I have colors and all those things, so I can sort of see. A human being is to see. A computer cannot see colors, right? How does a computer know that you are in this cluster and your friends also have that same cluster? So that you will know when I discuss unsupervised clustering. So the computer has a way that it will immediately tag all these points after it has been projected. It will tag all these points with, let's say, group 2. This will all tag this point with group 1, group 3. So computer will know, because there's no human being, right, looking at the picture and then telling you, if you like this book, you like that book. So that is unsupervised. Followed by this, you have to have unsupervised machine learning in order to do the classification by the computer alone. Then the other issue is that, I gave you an explanation of what the U and V means, and then how the components, the values that are actually transmitted. And this is what, in terms of the pictures, I think need about 20 to preserve top 5 features, let's say. And what you want to do is to make the accuracy of transmission. If you wanted to use it for communication, then you want to use that accuracy by 90% or so. And this is your sigma 1. Remember sigma 1, sigma 2, all those things. So you will have to take a square of that and take a square of that. Remember, it was square root of 10. So now it will become 10. And this was 10 when you had just 1. But otherwise, you will take the square and you want to make it, because if you sum them all, it will be 1. But if you will be summing a few of them and make sure that at least you transmit 90% of the information. Otherwise, it is sort of... And there are many other techniques that people use that have different names. But this linear discriminator is another one that people use. There's a lot of these. But the thing is, just learn one. And then next time you look at the literature about this, just first ask, did they do singular value or did they use some of the other techniques? And then you can then move ahead and do these things. So let's go through a few questions. Then let's see whether you remember some of these things. Maybe we can go ahead. Yeah. What is the first one? Singular value decomposition.
Oh, it's singular value decomposition is giving you a matrix with diagonal components, so you have a single measure in that sense.
No, yes. First of all, you are right that it is the sigma matrix, but the reason it's called singular is because it comes from the analogy of a transfer function where it's like a resonant LC circuit. Anytime the circuit is resonant, you remember that 1 over omega L minus 1 over omega C. So that's when the impedance becomes 0. So singular value simply means the point where the matrix, transfer matrix becomes singular. So this name has that historical analogy. But in principle, you get the idea that is the biggest component. What is the next one? Physical meaning of U and V. V is used to do what? Rotating the matrix, right? Remember the cosine theta and all. And U is used to do what? The projection of the matrix. All right. What about the next one? How many should you keep? And so this has to do with this criteria, that you should keep enough so that you can give 90% of the vectors is transmitted. 85, 90, whatever is the criteria. So this sigma, you have to look at the diagonal elements of the sigma, and from that add it up to see where they are. Singular value, what could be it?
The disadvantage.
Yeah, disadvantage.
It's considering only, because it's projection based, possibly it's considering only along the one component and you're ignoring some.
So you are always losing some information. This is true. The main thing, however, is that too much computation. If you try to do SVD, that's why Amazon gave that $1 million out, but they could never use that algorithm. They only wanted accuracy from 35% to 40% accuracy. But they got it. The people, their teams all over the world, from India, China, everywhere, the teams joined that effort. And the winning entry, as far as I remember, was singular value decomposition based technique. But at the end, they could not do it because it was just too slow. Okay. So in that way, machine learning is a statistical approach, which we'll be talking about in the next class. That's better in that way. What applications we are other than classification? So one is obviously the data compression. You can compress data or compress a picture and then send it somewhere at a lower resolution. Huh?
Or even encryption? Maybe?
Encryption, of course. You can do encryption also. But encryption, there are two types of encryption. One is that lossless, meaning that you can exactly reconstruct it back. Another is lossy encryption. So lossy means that and in that way it would be similar. Singular value would be similar. All right. And can you do singular value decomposition in Excel? For Wolfram Alpha, for sure. Excel, I don't know. You'll have to tell me that. I think there are all these packages in Excel that you can download and install. If you find one, send me an email, because I like to do things in Excel because Excel is so widely available. Sometimes people may not have MATLAB. MATLAB is expensive. Okay. Now, one thing is that you should look at some of the things. Although it's one lecture, there's a huge amount of reading goes behind the lecture. So therefore, you should look at some of these lectures, some of this information, especially linear discrimination analysis. This was done by Fisher. He invented it. So I think this is another way of doing principal component analysis. So you should take a look. All right, so that's all I had today. In the next class would be the artificial neural network. And you realize there's nothing neural, nor there's nothing artificial about artificial neural network. It is just a marketing thing. I shouldn't say this.